Hey there, folks. So far in this series, we've set up a Home Assistant instance on Hyper-V and installed a handful of add-ons that I consider essential. In this video, we are going to disassemble a Sonoff S31 IoT smart plug and flash it with custom ESPHome firmware. This will enable fine-tuned control over the device's behavior in Home Assistant. Let's get her done. To complete this process, I'll be using the following items: a Sonoff S31 smart plug, a set of hook-to-hook silicone test leads, a USB to UART development board, a Surface Pro, though this particular device isn't required. It just happens to be the easiest computer for me to use to perform the flashing. You can use any computer with a USB port. A USB-C to USB Type-A hub. This is also required for me since the Surface itself doesn't have Type-A USB ports. This model is a Ugreen 10G hub with 2 Type-A ports and 2 additional C ports. A mini screwdriver with a CR-V5764 flathead bit, as well as a CR-V PH0 Phillips bit. And a USB Type-A male to micro USB cable that is capable of both power and data transfer. With the prevalence of USB charging cables, there are many types of cables that aren't wired to support data transfer. This cable needs to support both power and data for the process to work. While I have 2 UART boards here, this is just to show some of the different options that are available. We only need one. The 2 UART boards I use for my projects are this Ximimark CP2102 board and this Mayina M-FT232 development board. The Mayina is a fancier product and has a 3.3 or 5 volt selectable power switch, right angle pins, and an integrated USB Type-A male plug on one end. This Ximimark is decidedly simpler, trading the integrated USB plug for a female micro USB port on one end, and even though it comes with the same right angle pins as the Mayina, you have to solder them onto the board yourself. Today, I'm going to use the Ximimark, but either of these devices work perfectly fine for the task at hand. Let's disassemble the S31 unit. A standard disclaimer would be that you should never do this with the Sonoff plugged into an active power outlet. I'm not entirely sure how you'd even go about disassembling the unit while it was plugged in, but please exercise some caution when performing these sorts of tasks. The Sonoff will get all the power it needs through the 3.3 volt lead we connect and the USB cable. I'll pick the unit up and, with my thumb, apply solid upward force on the long seams between the white body and the gray bezel. Next, I'll carefully insert the tip of the flathead bit into the back seam and gently slide the bit back and forth. Once I can feel the 2 pieces start to separate, I'll apply additional upward force with my thumb to create a bit more space. While holding the upward position on the long seam with my thumb, I'll insert the bit into one of the short seams and run the bit back and forth. I'll do the same thing on the other short seam. This is typically all it takes to separate the latches, which will allow the gray bezel to be lifted off. And that's the most difficult part of the disassembly. One thing to be mindful of when reassembling the unit is that while the gray bezel may look like an equal-sided rectangle, there is actually a slight pinch on the front edge length. When snapping the bezel back on, you'll want to make sure it's oriented correctly, otherwise you could break the latching posts. Next, slide the 2 edge covers toward the open side to remove them. This will expose 3 small Phillips screws, 1 on the top and 2 on the bottom. I'll insert the mini Phillips bit into the screwdriver and remove all 3 screws. Once they've been removed, I'll grip the outlet power blades and pull on the front cover to fully separate the unit. And with that, the disassembly is complete. On the side of the unit, there are 5 points of interest. First is the power button right in the middle of the PCB. We'll need to press this button and hold for a few seconds to put the device into flash mode. The other 4 points of interest are the solder pads on the left side of the PCB with the following labels: VCC, which stands for Voltage Common Collector or Common Collector Voltage, and is the pad that we'll supply 3.3 volts through. RX, which stands for Receive, and is the pad through which the UART programmer will send instructions into the device. TX, which stands for Transmit, and is the pad through which the smart plug will send data back to the UART programmer. And finally, GND, which stands for Ground, and to which we will connect the ground from the UART programmer. Holding the UART pins up to the side of the plug, here's the connection pinout we'll use. 3.3 volt on the UART will connect to the VCC pad on the plug. Never connect the 5 volt lead to the Sonoff plug. That can irreparably damage the device. RXI, or receive on the UART, will connect to the TX pad on the plug. TXD, or transfer on the UART, will connect to the RX pad on the plug. And GND on the UART will connect to GND on the plug. Be sure you are using the RX and TX pads on the Sonoff plug and not the D-TX and D-RX pads. To make these connections, you can, as I have many times, solder a small wire between them. This will work just fine. However, it is more work than necessary since we only need a hard connection the first time we flash these devices. Subsequent firmware flashes will happen OTA, or over the air, meaning the packages will be delivered over the wireless connection to the device from Home Assistant. Of course, if you totally bork the device settings remotely and need to low-level flash again, you'd need to disassemble the plug and go through these steps again. You cannot trust me when I say that I've never done that. Rather than solder, I recommend to use these hook-to-hook silicone test leads. They have a plunger on one end of each lead that, when pressed, will eject a metal hooked end on the opposite side. We just need to temporarily secure these hooks to the solder pads on the smart plug and around the right angle pins on the UART. This is a much simpler solution for the initial flash and are great to avoid the process of soldering and desoldering temporary wires. It doesn't matter what color lead you use on which pads, as long as they connect the points I laid out earlier. To connect a lead to the UART, I'll press on the plunger, slide the hook over a right angle pin, and let the plunger go. To connect the other end of the lead to the Sonoff plug, I'll hold it up on an end, press the plunger to push out the hook, slide it over the correct pad, and gently let the plunger go. While these connections aren't strong enough to withstand rough handling, as long as you are gentle, they'll stay in place for the flashing process. Let's get everything connected. First, I'll connect the micro USB cable to the UART. Next, I'll connect all the leads to the UART programmer. With each lead connected, the UART pins look like this. I'll then connect all the leads to the Sonoff plug. Once they are attached, it looks like this. With the leads attached on both sides and the micro USB cable plugged into the UART, our physical environment is ready. I tend to lay things out like so, with some masking tape on the cables to prevent any jostling movements. Now it's time to hop over to the computer and set up the flashing environment. I'll start by describing at a high level the strategy I employ for flashing these devices. I prefer to flash my smart plugs in an environment that is separated from the network they will ultimately run on. This allows me to flash and test a new device in isolation. Once it's functioning exactly how I want, I'll migrate it over to my real network. When it comes to flashing these plugs, some folks prefer to do everything directly in Home Assistant, while others use the internet site web.esphome.io. My process isn't the fastest way to go about flashing a Sonoff, but it is the method that fully satisfies my procedural sensibilities for viability and reliability for the task at hand. First, I'll right-click on the desktop and create a new folder named Configs. The ESPHome dashboard will create its configuration YAML files in this folder as I'm flashing the smart plug. Next, we'll download the drivers for the Ximimark UART. Every UART serial programmer I've ever used has required drivers, and this Ximimark is no different. I'll open a browser, enter CP210X, Universal Windows Driver in the address bar, and press enter to perform a Google search. This URL at the top, which is from Silicone Labs and references the USB to UART bridge VCP drivers, is the one we want, so I'll click that link. I'll drop this URL in the video description. Once the page loads, I'll click the Downloads tab, scroll down to the Software section, click the CP210X Universal Windows Driver package, select the desktop as the download location, and then click the Save button. The next piece of software I'll download is ESPtool, which I use to analyze Sonoff plugs before putting ESPHome on them. I'll place my cursor back in the address bar, type ESPtool, and press enter. We're after the Espressif/ESPtool serial flashing utility from GitHub, so I'll click that link. I'll put this URL in the video description as well. Once the GitHub page loads, I'll click the 5.1.0 release link on the right side of the page, scroll down to the Assets section, click the ESPtool Windows distribution file, and also save it to the desktop. There might be a different version of this tool released after I post this video that behaves differently, but 5.1.0 will work for what we need. The last software package we'll download is Python for Windows. I'll click back into the address bar, type Python download, press enter, and click the Download Python link from python.org. This is a good time to also mention that I'm not the kind of person who updates or uses newer revisions of software packages just because they've been released. Python is constantly evolving, as are the other pieces of software that are utilized in the flashing process. Updating a dependency package just for the sake of it can sometimes have unintended consequences of the negative variety. I've tested a lot of different Python versions, and at the moment, my process uses an older distribution of Python, version 3.13.4 to be exact. So rather than downloading the newest version, I will be downloading and installing 3.13.4. On the Python page, I'll scroll down to the Looking for a Specific Release section, scroll inside the box to find version 3.13.4, click that link, scroll down the release page to the Files section, click the 64-bit Windows installer link, and download the file to the desktop. For the moment, we're done with the browser, so I'll go ahead and close it. The UART driver will be installed first. I'll extract the contents of the CP210X archive to a temp folder on the desktop, double-click into the temp folder, right-click on silabser.inf, and click Install. Once finished, I'll close the install confirmation message and delete the driver temp folder and zip file from the desktop. Next, I'll extract the esptool archive to a temp folder and then delete the archive. The last install is for Python, so I'll double-click on its installer next. I'll check the two boxes at the bottom of the setup window to use admin privileges when installing py.exe and to add python.exe to the Windows system path. Next, I'll click Customize Installation. The options on this screen will all be left checked, and I'll click the Next button. I'll check the Install Python for all users checkbox, and then click the Browse button to specify the install location. By no means do you have to select the same folder that I do. This location is just my preference for organization. I'll expand this PC, expand the C drive, expand the _programs folder, right-click the programs folder, and create a new folder named Python. I'll select the newly created Python folder and click OK. And finally, I'll click the Install button to make it all official. Once the setup is complete, I'll close the installer. We're done with the Python setup file, so I'll go ahead and delete it. Since the Python installer adds a new entry on the Windows path, at minimum, I'd recommend logging out of your Windows account and then logging back in. However, I prefer a system reboot in these situations, so I'll go ahead and do that now. Once we're back in Windows, I'll click the Start button, search for Command Prompt, and press Enter to open the app. The first command I'll run is to validate that Python has been successfully installed. At the prompt, I'll type Python space -- version and press Enter. If we see Python in the version number, then it's been successfully installed. Next, we'll install a handful of dependencies. I'll type pip3 space install space wheel and press Enter. After a few moments, the wheel dependencies will be installed. Next, we'll install ESPHome by typing pip3 space install space ESPHome and press Enter. There's a number of additional packages that ESPHome relies on that will be installed, so this one will take a little longer. With ESPHome installed, I'll type CLS and press Enter to clear the screen and start afresh. We are now ready to proceed to analyzing and flashing the firmware, but that requires the Sonoff plug to be in flash mode. To do that, we're going to return to our physical setup and perform the following actions. Press and hold the power button on the side of the Sonoff plug. This is done before connecting it to the PC. With the power button pressed and held in, connect the micro USB cable that's connected to the UART programmer to the computer. In my case, I'm plugging it into the USB hub. After a few seconds, you should hear the Windows device connected sound jingle. Once you hear that sound, continue holding the power button on the Sonoff plug for 5 to 7 seconds. After that amount of time passes, let the power button go. And that's it! The plug should be in flash mode, and we're ready to move back to the PC. You'll need to put the Sonoff into flash mode a few times throughout this process. Moving forward, for simplicity and to conserve some video runtime, I'll simply say put the Sonoff into flash mode, rather than repeating the steps that were just outlined every time. Back on the computer, I'll double-click into the esptool folder on the desktop, double-click into the second level folder that contains the esptool application.exe, click into the Explorer address bar, and press Ctrl-C to copy this folder's file system path onto the clipboard. I'll click back over to the command prompt window, type cd space, and right-click on the command window with my mouse. This pastes the full path of the esptool folder from the clipboard to the command line. I'll press Enter to change the working directory path to the esptool folder. Next, I'll type esptool space flash-id and press Enter. This will query some details about the onboard flash module on the Sonoff plug. First, it will tell us if the device was actually in flash mode. If it wasn't, none of this information would be retrieved and the connection attempt would fail. Second, it tells us the chip type, which is another method of confirmation that it is in fact an ESP-based microcontroller. Third, it tells us the MAC address of the unit, which can be handy if troubleshooting connection issues through your router's connected devices page. And finally, it tells us the size of the onboard flash memory. This is a useful bit of information since the board definition in the device's ESPHome YAML file can have an impact on the amount of flash memory that can be used by the firmware flashing process. After taking note of all these details, we're done with the esptool application. We're now ready to flash the Sonoff, but since a hard reset command was issued automatically by esptool when we queried the device, we need to unplug the USB cable from the computer and reattach the device in flash mode. Follow the previously outlined steps to do so. I'll close the esptool folder and then double-click the configs folder on the desktop so we can monitor the files that are created throughout the flashing process. The first command I'll type at the prompt is one that sets Python's encoding format to UTF-8. This helps to avoid erroneous warning and error outputs when viewing ESPHome's log output. At the prompt, I'll type set space Python IO encoding equals UTF-8 and press Enter. This command helps to avoid these sorts of nastygram log warnings later in this process. Then, I'll press and hold Shift on the keyboard, right-click the configs folder on the desktop, click Copy as Path, click back into the command prompt window, type ESPHome space dashboard space, then right-click the command prompt window to paste the configs folder path onto the end of the command, and finally press Enter. This will start the ESPHome dashboard, and since we passed the configs folder path at the end of the command, ESPHome will use this folder as its file repository. Pretty nifty. Once we issue this command, we'll see a message in the command prompt window that the dashboard web server was started on 0.0.0.0 with an access port of 6052. 0.0.0.0 is a meta address that essentially makes good and sure that the dashboard is accessible over any network interface the machine might have, and does so on port 6052. To start the dashboard, I'll click the Chrome shortcut in the taskbar, enter localhost, 6052, and press Enter. This will open the ESPHome dashboard. Moving forward, the command prompt window will output a sort of processing log as we take actions inside of ESPHome, but it's not strictly necessary for us to see. I'm going to activate and minimize the command window since we don't need to see the output. Before we flash the plug, I'm going to make some changes to the ESPHome dashboard secrets file. To do that, I'll click the secrets link in the upper right corner. This is not Home Assistant secrets file, but a separate file specific to this ESPHome dashboard. The purpose of secrets is to store usernames, passwords, and any other details you'd like to reference within the device-specific YAML files that you also don't want to include in those files directly. There are a number of different reasons why this approach might be, and is often preferred. The format of the key value pairs is keyname, space, and then the value. To create a comment line, use the hash or pound sign. The first entry I'll put in secrets is my test network's SSID name. I'll enter Wi-Fi _SSID space, and then in quotes enter the exact name of my test network. Misspelling or even miscasing the network name can cause issues with the device connecting to your network successfully, so be sure to get this right. The second entry I'll put in secrets is the password that corresponds to my test network. I'll enter Wi-Fi _password space, and then in quotes enter the exact password to the Wi-Fi network. This is another thing you'll want to get right. I'll also add a network details section that contains entries for the network's gateway IP, subnet mask, primary DNS server, and secondary DNS server. These are details that are going to be changed very, very rarely. But if they were to change, I'd want to change them in one spot and have them dynamically cascade down into all the device-specific YAML configurations. This is one of the many benefits to storing these kinds of things in the secrets file. Once done, I'll click the Save button in the upper right corner to save the file. You'll notice that upon saving, a secrets.yaml file is created in the configs folder. Later in this video, we'll duplicate these details into Home Assistant. To close the file in the dashboard, I'll click the X icon on the left side of the secrets header. In between takes for this video, I realized that I forgot to download my code template that I use when flashing, so I went ahead and downloaded that file and placed it on the desktop. It's also linked in the description of this video. Next, I'll click the New Device button, click the New Device Setup option, and enter D-Media Center-Sonoff-S31 for the name. While there isn't a text limit on the name input box, the compile operation will fail if you specify a name that is longer than 31 characters. Keep that in mind when choosing the name. I'll click Next, and since the Sonoff is already connected in flash mode via the USB cable, I'll click the Connect button. If your device is not connected in flash mode, you'll need to do that now. Chrome will ask us what serial port to connect to, so we'll select the UART bridge controller, and then click the Connect button. Your programmer might have been installed on a different COM port than mine was, but that's just fine as long as the driver is installed, and Chrome sees it as a connected serial programmer. You'll notice that new files have been created in the configs folder, including a device-specific YAML file. The dashboard will now download, compile, and flash the ESPHome firmware to the Sonoff. Once the flash operation has finished, the configuration YAML will have been created, but the newly flashed device will not find its way onto the network. This is okay. Go ahead and click the Close button. The dashboard shows our device is offline, which is expected, but we can now edit and interact with the device-specific YAML file in ESPHome. I'll click the Edit button on the device card to open the device YAML for editing. One thing I'd highly recommend you think about as you evaluate the security posture you'll adopt for your own devices is that when you flash a new plug and are in the process of configuring it, always jot down the encryption key and OTA password and temporarily store those someplace separately, at least until you decide whether you want to use them and how you use them. Rather than type a whole bunch of code manually, I'm going to make use of my generic code template. I'll open the blank template YAML file I've placed on the desktop, press Ctrl-A to select the full contents of the file, press Ctrl-C to copy the contents, close the Sublime window, click back over into ESPHome, press Ctrl-A to select everything in this file, and then press Ctrl-V to paste the template code into the window. As a reminder, this code is linked in the description of this video. There's only a few modifications that I'll make to this code before flashing to the device, but I'll take this opportunity to explain a few concepts that I've used in the code. On the offhand, it might help someone out there on their own journey. A quick note about the YAML alright is that it's the end result of lots of reading, conversations I've had, scouring of forums, and testing. But I don't have a techno-bibliography for where I got each setting. It's not my goal to pass this code off as being exclusively my creation, but it has been extensively tested to meet my needs. I like to make use of YAML substitutions to make it easier to organize the contents of each file. With substitutions, I can place everything that I consider editable at the top of the file, so I don't have to be scrolling the full contents to find the values I want to change. This saves me time and reduces the likelihood of me forgetting to change a value when I'm deep in an editing session. Also, when editing YAML, be very careful with the formatting, as even a single character mistake can lead to a compile failure, though ESPHome and Home Assistant provide some guardrails to help protect against this. Let's start by replacing the placeholder values in the substitution section. For the static device IP, I'll specify the IP address that I want to assign to the device. I'll enter 10.1.10.202, since that aligns to my test network. For the device name, I'll be very careful to enter the same name I specified for the name when adding the new device earlier, which is D-Media Center-Sonoff-S31 in all lowercase. For the device-friendly name, I'll enter the same but slightly cleaner name, D-M, Media, C, Center. For the device comment, I'll enter a brief description of what this device will monitor. That just happens to be the current, power, and voltage of the Media Center computer. And for the captive portal SSID name, I'll enter D-Media Center, fallback SSID. Keep this name to no more than 31 characters as well. The way that substitutions work is that the key names here can be referenced in the YAML file using the format of $, curly brackets, and then the key name. For example, the key name device_name in the substitution section is referenced in the ESPHome section using the $, curly brackets, and the name used in substitutions. To reference information in the secrets file from within the device's YAML code, use the format !secret space followed by the key name used in the secrets file. Those are the changes I'll make to the initial YAML file, so I'll click the Save button in the upper right corner, and then click the X button on the left side of the header to return to the main dashboard. Now that we've edited the YAML file, we can validate the syntax by clicking the 3 vertical dots, and then click Validate. While the validation may not catch every permutation of error, it does a great job of evaluating the YAML code for syntax errors. We have a green checkmark after performing the validation, indicating that the code syntax is valid. Since the plug is already connected to the computer and is currently in flash mode, I'll click the Install button in the lower right corner to reflash the device with the updated code. For the flash method, I'll click Plug into this computer, select the UART, and then click the Connect button. After a few moments, the updated firmware has been flashed to the device. I'll click Close on the Configuration Installed modal. Now I'll unplug the USB cable, wait a few moments, and plug the cable back in without putting the device in flash mode. In short order, the device comes online in the ESPHome dashboard. We can now click the Visit link on the device's card to open its local portal. I don't use the device-specific portals very often, but they are there when the need arises. To return to the ESPHome dashboard, I'll click the X on the Device Portal Browser tab. The device card now has a better friendly name at the top, the correct host name and YAML file name in the middle, and a brief description of what this plug measures. We're now at the point where I will migrate the device over to my test network's Home Assistant instance. If migrating a device between networks that have different IP address or subnet formats, I'd have to first flash the device once more with the static IP address that would ensure that the device came online without any issues. First, I'll shut down the ESPHome dashboard we've used to flash the device by reactivating and then closing the command prompt window that was used to start the dashboard. After that, I'll unplug the USB cable from the computer that connects the UART to the computer. Next, I'll start the Home Assistant instance on my Hyper-V test server. Earlier in this video, I mentioned that I prefer to shut down Home Assistant while I'm provisioning a new device. Back in Chrome, I'll enter the Home Assistant URL of http://homeassistant.local:8123 and press enter. Then I'll enter the username and password, and once logged in, click the ESPHome Builder in the left nav. Before finishing the device setup in Home Assistant, I'll go ahead and reassemble the Sonoff. The steps to reassemble the plug are to line up the power blades with the plastic housing shell, press the 2 pieces together, reinsert all 3 of the small Phillips screws, slide on the edge covers, and snap on the gray bezel plate. Next, I'll insert the plug into an open electrical outlet and plug the Media Center computer into it so we can see some basic monitoring values. Since this is the first time adding any device into Home Assistant, I need to make sure my ESPHome secrets file inside of Home Assistant matches what was set up in the ESPHome dashboard we use for flashing. To achieve this, and to copy the Media Center YAML file to Home Assistant, I'll use the Samba Share add-on that I installed in the last video of this series. To access the network share, I'll double-click this PC on the desktop, click into the address bar, enter the Home Assistant server IP, and click Enter. I'll double-click into the config folder, and then click into the ESPHome folder. Now, I'll copy the secrets.yaml file from the configs folder on the desktop into the ESPHome folder, and then move the Media Center Sonoff S31.yaml file from the configs folder into the ESPHome folder. In short order, we can see the Home Assistant has pulled in the config and the device is online. I'll click the Visit button on the device's card. We now have an output relay switch that, if clicked, will cut electricity to whatever is plugged into the Sonoff. We can also see the network information, as well as entries for current, power, and voltage. There's also an output log on the right side of the window that will update as the Sonoff processes new data to the UI. There's one more thing I'd like to show you, and to do that, I'll close this tab to return to Home Assistant. All of the firmware flashing we've done so far has been with the USB cable attached, but now that the plug is closed up, we'll rely on OTA, or over-the-air, to wirelessly push new firmware or code builds to the device. To edit the code, you'll use the same Edit button on the device card, and clicking the three dots also shows the validation and install options that were present in the dashboard. So the process now will be edit the code, validate the syntax, click Install, and now select wirelessly as the distribution method. The firmware package will compile and then be pushed out to the device. Once it's complete, you can click the Stop button to close the window and return to the ESPHome builder. Well, that's going to do it for this video. I hope there's been something of value in observing how I prep, flash, and configure an S31 smart plug. There's a lot you could modify in the device YAML to change its behavior, like adding new sensor references for power factor or apparent power, but since I don't use those, I remove them from my YAML code. As I mentioned earlier, this is not the fastest way to go about the process, but it is how I like to go about it. In the next and final video in this series, I'll show you how I create some simple performance charts in Home Assistant for monitoring the equipment that are connected to these plugs. I hope you've enjoyed this demonstration. Thanks for watching, and out.